Welcome back, people. I've got a lot of updates to share with you. We'll go over those in the stream. We're going to add weights and biases to our code. We'll have a discussion on the new model, a little bit comparing with the AlphaZero model. Well, I was watching G-Hot stream, and there's something called denormalized layer, so we'll go over that, and we're going to read a lot of papers. So it's a fairly long stream, so let's begin. So the first thing I changed was now we support HTF5 file format and NumPy zip file format. And the reason we have done that is if you go over the raw code, the first code, which was basically load the language model file, which looks something like this. It's a very long file. Each row is basically one game, and each row is one game, and each row has space separated strings or numbers which need to be converted to integer, and it's all consolidated into a very long string. So all these lines might be consolidated into a super long string, and they're separated by the game tag. So you can look here. It's separated by the game tag, and then we convert this to basically a 2D array. This super long array is converted into a 2D structure with some certain total data size and some maximum length. This then split into test and training sets and return. So the problem with this is you can understand that if I'm going to load all these files, it's actually super slow. So what I've done is I've converted this to HTF5. We'll quickly go over what HTF5 file format is. So HTF5 is a hierarchical data format. Is a set of file formats designed to store and organize large amounts of data. This was initially funded by a lot of different organizations, but finally was picked up by NASA. And the main advantage this particular file format has is that it's used to store a lot of numerical data, which is something very similar to our case. But there's another problem with HTF5 for which I finally started using NumPy zip file format. The reason is that HTF5 stores the entire data set on disk, and it only loads the indexes and basically the locations of different arrays on the memory. So anytime I actually have to fetch an array, which happens here, .get item, what's going to happen is it's going to go to the disk, load it from there, convert it, perform some conversion, and then return it to and then send it to data. So the time that it takes to actually load from disk is significantly higher than just storing this entire thing in the RAM memory. So this is where the NumPy zip file format actually used. What you do is you store this entire thing in the .npz file, and you simply load it, and boom. So this process actually takes about 16 seconds to load this entire thing into memory, compared to approximately 15 to 16 minutes to load this way. So now you can see it's pretty fast. It's way faster than 15 to 60 minutes. It's approximately 16 to 20 seconds now. So the first thing we need to do is we need to add this thing to a compile file, a download.py file, which has all the information on this process. So I've already added the .compile thing, which a compile flag, which you call, and it compiles the entire dataset into HTF. So what you're going to do is we're going to add another thing in here, which is the file format that you need. So let's start. So this subroutine basically compiles the data set into HTF5 or NPZ file format. So for this we need what is going to be the file format. So say argv 2. Now there are two processes that we have to do. One is we right now I've hard coded it to 85, so we'll need to switch that. So what you're going to do is this thing is going to be the maxlen int and the other is going to be the format, which is sys dot argv3. If so, either way we have to do this entire process. So this max len, I should put it in place here. Okay, and this process is format independent, so we'll also move this thing here. Okay, perfect. Now we convert it to formats, which is if format is equal to hdf5, then we run this entire process, which is creating the file, adding the subgroup, and closing that file, creating the dataset. Lf format is equal to npz. Then what I'm going to do is I'll just copy paste the code from. Yeah, another thing to note is the early stopping function. It actually works pretty well. So you can see it. This is my cloud. You can see it's saying no improvements for past 3 evaluation, and it stops the training, but the patience is actually 0.3. Patience is actually 3 steps. So I'll simply add the numpy code. Yeah. So we need to open it. Actually that's it. Print saving file at saving numpy zip at and for this we are going to say print saving hdf5 at this thing. Cool. So we have updated download.py. I've also updated the file formats here. Now notice for your use case you might have to actually change this right now, because the dump I've taken it at 85 as the sequence length, so it's hard coded at this thing. And the other piece I've added is I've added a bypass here which handles the different formats. So if it's an HDF file format, it's going to load it this way. If it's NPZ, it's going to load it this way. And once I have the LMs and the results, it now basically is you just need to send this thing to the loaded dataset and it works. So the difference it has made is significant. Now each file process is actually taking, let's so now you can consider it like this. Each process, each iteration was taking this much seconds cross 256 something, right? This much time, and now each iteration is taking this much time. And let's see how much saving that actually is. That's 16% time saving, right? It's super significant. And moreover, even the initialization of this process, it's far better than with HDF5. No, HDF5 actually loads faster because it does not have to carry anything. But you know, the numpy actually takes 20 seconds to do that, and it's a good trade-off. Another thing I really wanted to read on is what exactly is pickle. I know a little bit, but I actually have not used this thing very well. Okay, the pickle module implements binary protocols for serializing and deserializing Python object structure. Pickling is the process whereby Python object hierarchy is converted into a byte stream. Unpickling is the inverse process whereby a byte stream from binary file or bytes like object is converted back into a object hierarchy. Comparison with Marshall. Python has more primitive serialization module called Marshall, but in general pickle should always be preferred to serialize Python objects. Comparison with JSON. JSON is text serialization format. It outputs Unicode text, although most of the time it's encoded as UTF-8, while Pickle is a binary serialization. JSON is human readable, Pickle is not. Of course, it's binary. Interoperable, widely used outside Python ecosystem, Python specific. Yeah, so this is like the main advantage you have. Pickle can represent extremely large number of Python types, many of them automatically by clever usage of Python's introspection facilities. Complex cases may be tackled by implementing specific object APIs. Unlike Pickle, deserializing untrusted JSON does not itself create an arbitrary code execution vulnerability, which happens with Pickle. And what is this? So what you're doing is you open some Pickle file and you read this. Now let's store the data. So first, okay, so I have Omkar, Jagdish. I have two dictionaries. I create a single giant dictionary like this thing, and I just save it, and when I load this data I can directly use it like this. Okay, so that's like the main advantage about this thing. Okay, let's go ahead. Next thing I want to do is, now I written a lot of things that we actually want to implement today. Just show it to you. So there are all these things. New model in push, explain AlphaZero model. I coded. I'll explain this thing and add a new model and add weights and biases. So what we are going to do is probably start with the model. Yeah. So I was going through the AlphaGo paper n number of times. Yeah. And what I wanted to know is what AlphaZero for chess is also an extremely strong player. It's a very good network, but what I wanted to know was how big it is actually. So I implemented a very simple AlphaZero code. Now this is wrong because it does not have any residual connections, but that's fine because I just wanted to know the number of parameters. So what you have is you have the input block, which basically converts the 119 channels you have. So I'll explain how that works. For each layer you have what is the P1 pieces, P2 pieces, and repetitions. So these are the number of planes you store for each input. Basically, what was each move? What was the piece 1, piece 2 move, and what are the repetitions? So you have these 14 moves per plane, and then you have 8 cross 8 for the board, and you store 8 step history. And these are all the single things, which is the color, piece 1 castling, piece 2 castling, and no progress count. So combined you have 119 features, handcrafted features that are input sent to the model. So in channels are 119, out channels are 256. Each block has a kernel size of 3 by 3 and padding is 1, because if you don't do padding 1, the output board because of the stride movement is actually is smaller, and we don't want that. Then you have batch norm and you have ReLU. Each block is 256 cross 256, basically the same thing, and you have 20 blocks for AlphaZero. Then for the now this is the entire body. This is what they call the residual tower. After the residual tower you have two heads, one is the value head and the other is the policy head. Let's go with the policy head first. It's much more simpler. You have another 256 cross 256 block, same values. You know what, actually it's not true. What you're going to have is this as well. Alright, and then the final output, as you can see here, is actually an 8 cross 8 cross 73 stack. So the output is 73. For value, what you have is you first compress all the channels you have to 1, kernel size this, and then what you get is an 1 cross 1. So the output you get is this, which is 1 cross 1 cross 8 cross 8. Board 1 is the batch size, This is the number of channels because I'm using PyTorch. The channels is actually the second dim, the height and the width of the input image, matrix basically. And so you get a 64 so then you have to convert it to linear. You get 64, the output features are 256. Then you have a ReLU unsimilarity, also non-rectification. Whatever, I think I did a mistake. Let's mastering go without human knowledge. Yeah. Where is architecture? Okay, yeah, this is the architecture. Rectify non-linearity 256, rectify non-linearity, and fully convert to scalar. So yeah, there is no batch norm between this thing. And you finally have one scalar value and you have the tan h value. So when you pass something, you get a model that's just 1.6 million parameters, which is amazing actually, that it can do this much in just 1.6 million parameters, whereas our model is actually much larger. It's approximately 6.4 million parameters. Now, why do we have a larger model? I think in our case we do need a larger model because we need to store the entire internal representation as well. Note that alpha models basically they receive a lot of handcrafted features, which is this domain knowledge. In our case, we do not give it any domain knowledge. What that means is it needs to have the entire understanding of what the board looks like, where everything is, what is happening internally. So you get now why this is not correct is because you need to add residual connections, but this is fine. I just needed to know how many parameters were in this object, in this model. So this is a model right now. What we have done is, what we had initially was something like this. I added I added on the things here. I added on the head. Initially it looked like this. So you have the entire GPT-2 body, and after the GPT-2 body you have one head that is directly telling what is the policy, just like what an actual GPT-2 looks like, and you have the same output values that are squashed to a flat scalar, that's squashed to a scalar, and this is called the value head. The difference now, what I'm trying to do is I'm trying to incorporate this particular feature here. What they have done is you have a very big residual block, which can be considered something like the main GPT-2 model we have. So you can consider this equivalent of the residual tower in alpha XX. Yeah, this is the main residual tower, and on top of that what we're going to do is we're going to implement this similar value heads and policy heads. Now note that policy head actually has the complete one more stack here, and it has another output stack. So we are going to do the same thing. What I've done is I've called the block from modeling GPT-2, which uses this same block internally. And for value, what we're going to do is we're going to call in MLP, which is nconfig.nempd, and yeah. So what this function does is it takes it basically first scales the value to 4 times NEMBD, and then brings it back to this particular smaller value, and it has a ReLU activation in between. So we are going to implement a similar thing. So you can see here that it actually goes from 256 to 64, and then 64 to 256 and 1. What we'll do is, so they do a compression kind of thing. So they compress the model to 64 parameters and then again to 256. Instead, what we can do is we can just scale this thing to 256. Whatever is the 4 times this thing, whatever is the output, we can then do a ReLU, and let's call it nn.ReLU, and our final layer is actually going to be just a linear layer that takes config dot and embed cross 1, and finally the tanh activation, linear, oh my god, whatever. Now if I give this thing the same number of layers, what it's going to do is that's not true. Now I need to compress the layers. I don't need this big of a model now because I'm going to add 2 blocks basically on top of it. So this config is actually going to be a duplicate of the config. So what we need is from copy import deep copy, or let's see. If I do model config and I just do vars model config, it automatically returns a gigantic array, gigantic dictionary. So what we can do instead is config is equal to model config vars self.config, but we are going to replace one thing, which is config dot num layers. This is going to be config dot n layer minus 2, and that's it. So the reason we have done it as minus 2 is we are already going to stack 2 policy heads on top of it. Now this is one block and this is another block. This, you can consider this as the final linear LM head. So this actually should be 1. So the policy head, so this is actually this thing, and what you're going to do is you're going to squash the linear head right here, which is nn.linear config.nembed. I do get the layer norm out here. You know what, we might have to actually hack through a little bit, because what it's going to do is it's going to return GPT-2 model output already has a layer norm implemented. So you can see the output of GPT-2 model already has a layer normalized, and whereas what block is going to do is block is going to again pass a layer norm here, and we don't want that. We don't want it to again pass through a layer norm. Which one should we implement? This thing? Let's see. Let's just implement the block. The block is much simpler. And so what we're going to do is we're just going to call it you know what, let me just zoom in class policy head. Let's just call this thing, and then dot module def init self config super dot init. So what this thing is doing is it has all these values, which is this, and we're going to directly copy paste them. And you also have an MLP. Now this is, we don't need this thing, we just need one layer norm. Just one layer norm would work. And for forward, def forward, what we're going to have is we are going to have the X, let's just call it the X, which is the output of this body. We're going to pass X through self.attn. and we don't need to do this. Yeah, let's just call it hidden states, it's much better. And we don't need any of this because it's useless. And then we have hidden states is equal to output attention output plus hidden states. This thing now simple feed forward hidden state, just add the residual connection. I think you can hear the kids, man. These kids, they're just, how much can you play? And we return these. So this is the block, and we are going to have policy lm head, which is nn dot linear config dot ne. And once you have the hidden states, all you have to do is you return self dot lm head and you pass hidden states to it. Okay, cool. So your policy head now is simply the policy head model. Pass it the config. Alright. Attention hidden size is basically config dot nembd. Context is the same thing. Scale is equal to false. Now, do we want it to scale? No. What is the default value for scaling? You have the block. You have the. Wait a minute. What? This is the block. This is the pre-trained model. And down here you have the block list. Scale is equal to true. Okay, so by default scale is equal to true. Okay. Similarly, hidden size is now config dot nembd. Inner dim is this thing cross 4 and config. Okay, perfect. And this is going to be config dot vocab size. Okay. So our policy head is now done. Yeah, perfect. And our value head is also done. Alright. Let's see. Okay, we don't need to do this. Attention is not defined. Okay, perfect. No worries. And we no longer need the block. Oh, so the model is now 6.5 million parameters. It's not a very big improvement. It's not a very what should I say? It's not too large. This should be fine. Let's just run something through here. So what we're going to feed it is torch.rand, and yeah, size is going to be the batch size is 1. Your total sequence length is 34, and yeah, that's it. Base HFGT object has no GPT. Oh, so the output is actually self dot body. This is -1. Okay, what is it saying now? Oh no, it's not going to work. Random low is equal to 0, high is equal to 100, and size is equal to 1 cross 3. Okay, attention output is not defined. What do you mean it's not defined? Outputs PUTS cannot concatenate list, only tensor. Policy head has no attribute ln2. Yeah, of course it doesn't have, it just has ln. Okay, perfect. So the model is now working. What we're going to do is we're going to call this thing, first this is commented, the policy head and value head are now similar to what is in AlphaZero. And let's just clarify here as well, AlphaZero. We're going to call this model 2. Now let's just call this thing beta 0. No, let's just call this beta chess. Why not? Okay, we need to add this thing to our main code base. Okay, people. We also need to add this. Wait a minute, I'm not calling Adam? What the hell? What's happening in training? Oh, it's calling directly torch.optim. No worries, let's just let it be. I have h5 by JSON time. Where's JSON being used? Oh, okay, perfect. So what are the changes? Yeah, I had a very stupid bug. I'm not even going to tell you about it, but it was super stupid, and we fixed that. So I used multi-step LR, but now what we're going to do is we're going to use a variety of schedulers from now on. And what we need to do is we need to have a better way of actually creating this model. So when I want to experiment with, say, a lot of different schedulers, then I should be able to do it at a single config file command. That's it. So I have a policy head, I have a beta chess. Okay, I also need some way to actually, we need to create a model much better way. So what you're going to do is, let's just commit this much, which is gst git add git commit add compile support for htf5 and npz plus new model. Yeah. We have added the new model. Now what we're going to do is we need to improve the train file. So the first thing that needs to change is probably this piece. In almost all my other experiments, I use this thing as name, which is a far better use. Alright, so args.name is going to be the new thing, and our model LR1, LR2, optim settings. Then you have the model things. Now Node, by default I'm already using this thing, which is .npz file. I also used it for my experiment, this thing. I'll also show you the results, but yeah, let's just go over the results first. Train results. These are the Q1 models, which use the old data set, and you can see that the value actually settles at around 0.61. This is not great, not bad. Let's just say this was good one. So A1, these are the files. Accidentally during logging I use the test slash thing. A are the models that are the new models that use the new data set. Problem is, you can see that the value actually collapses to 0.84 somewhere around above 0.8, roughly about 0.8. Even though the loss is actually decreasing. And now I'll show you what happens with A2. And A2, so A2 was the step scheduler function, step scheduler method. You can see we start off with 3 minus 4, that is 0.0003. As it reduces, it hits the gamma of 0.01, again the gamma of 0.02 at 1000 and 2000 steps. At 6000 it reduces further. This ain't very good. This ain't very good. And then I have the A3. Yeah, this one actually uses the multi-step, where is it, one cycle LR basically. You know what, we are also going to read a lot of papers today, so we'll cover that. Now you can see what is happening here is that it learns pretty well. The value is somewhere below what this model is saying, but as soon as the around say 6000 steps, you can see as the learning rate actually starts to decrease, the value actually starts to increase. And this is where approximately at 8k steps the model automatically stopped. So you can see it saw no improve for past 3, which means this thing around 7.5, 8k, 7.5k and 7k. So what it saw at 6.5k was the best value, best loss, after which it did not see good loss, which in our case would be approximately here. That is the best loss, was actually 3e minus 7. Alright. No, sorry, not 3 minus 7. This was actually 0.0045. Tad below 0.005 where I actually wanted it to go. Another issue is that the accuracy continues to stay 0. Yeah, so these were the results from this run. It took about 2 hours 7 minutes to run on a 2080 Ti setup, two 2080 Ti chips. Yeah. Coming back to this, what we are going to do now, you can see that here we need to experiment a lot with different values, and so we need a proper test bench kind of setup, and so we're going to use that. So first thing we need is, what are the exact models I want to use? Add argument, model type is equal to string, action, default is beta, which means the beta model. Help which model to train. Select from base. Oh god, where we go? Select from base and beta. Okay, so we have now added the model. Now we also need the optimizer setting. Args dot add argument, optim type is equal to string, default. No, wait, we don't need the optimizer, we actually need the scheduler method, and this is part of the training. So default is equal to none, help which learning rate scheduler to use. Yeah, and now we need to add certain checks. Add checks. Oh my god, should we add them here? You know what, let's not add any checks. we'll just directly add it here. If args dot model is equal to beta, what we say that mod, and what we're going to do is we're just going to import star. It's so much more simpler. Beta, then model is equal to beta chess and model config. Well, yeah. Elif args dot model is equal to base, then this thing, and what we're going to say is else raise value error found wrong model. Model name args dot model. Okay, perfect. So now get the model size, and we need to add the trainer setup, which scheduler to use right here inside the training config. So we go to the training setup, we use the scheduler as none, this thing as scheduler, and we add it right here is equal to args.scheduler. Now we go here, set up correct scheduler if config dot scheduler. We also need a scheduler dictionary. So these are all the schedulers that are supported. The problem with schedulers is we also need to pass them all the parameters we need to use. So you have simple schedulers like lambda. These are optimizers, sorry. Yeah. You have a lambda LR, which you basically give it what was the epoch, and it returns the multiplier, basically what multiplier you need to use to apply to the learning rate right now. So in this case it's basically 0.0095 to the power epoch. What does it actually look? So, yeah, that's simple, no worries. Then you have the multiplicative LR, you have the step LR, and you have multi-step LR, exponential LR, cosine annealing LR. Let's just open these papers because we'll be going over them. Alright, you have the reduce LR on plateau, reduce learning rate when a metric has stopped improving. Models often benefit from reducing the learning rate by a factor of 2 to 10 once learning rate stagnates. The scheduler sends metric quantity, and if no improvements is seen for a patient's number of epochs, learning rate is reduced. How does it work? Min. Note that this step should be called after validate. Capacity validation loss. Factor. Default is 0.1. Mode. Min max. In min mode, LR will be reduced when the quantity monitored has stopped decreasing. In max mode, it will be reduced when quantity monitored has stopped increasing. This is actually pretty smart. This is very smart that you simply send it whatever value you want to send it to. Whatever value you want to send. The problem is that we do not validate in every epoch. Because in these kind of language models you have like one test loss and you have train loss. That's it. There is no validation loss. Yeah, super convergence. We're going to read this paper. Right now I'm using this one. In practice, I've seen that this one works pretty well. But the GPT-3 paper, they actually use a different kind of scheduling. Language models of few short learners. Yeah. So this is the GPT-3 paper. This is actually search schedule learning rate. Learning rate. .60 minus 4, which is basically 6. You can actually create a nice plot from it and understand what is happening. I love how even the small model is just 125 million parameters. No. Small learning rate. To train all versions of GPT-3, we use Adam with beta 1 0.9 and beta 2 0.95. We clip the global norm of gradient at 1.0. We use cosine decay for learning rate cosine decay for learning rate down to 10% of its value over 260 billion tokens. After 260 billion tokens, we continue the training. It continues training at 10% of the original learning rate. There is a linear LR warm up over the first 375 million tokens, but we gradually increase the batch size linearly from small value to full value over the first 4 to 12 billion tokens of training, depending on the model size. What does that mean? We also gradually increase the batch size. So first 375 million tokens. 375 million tokens. So the batch size is 3.2 million and okay. Data are sampled without replacement during the training until an epoch boundary is reached to minimize overfitting, of course. All models use weight decay of 0.1 to provide a small amount of regularization. During training, we always train on sequences of full context, token window, token context window, packing multiple documents into a single sequence when documents are no shorter than 2048. In order to increase computational efficiency, sequences with multiple documents are not masked in any special way, but instead documents within a sequence are delimited with special end of token text, giving the language model the information necessary to infer the context separated by the end of text token is unrelated. This allows for efficient training without the need for any special sequence specific masking. Yeah, the sequence specific masking, it doesn't actually work. So anyway, they use cosine decay. Let's just go over all the papers and see. So stochastic gradient descent with warm restarts. This is cyclic learning rates. This one uses the cosine decay, and this is the superconvergence paper. Okay. So you see, this paper actually came out from the US Naval Research Lab, and this paper as well actually came out from the US Naval Research Lab. This gives you, it's by the same author actually, but it gives you an idea of what kind of work they're actually doing. So this happened across 2 years, but the paper was submitted in 2015. This was submitted in 2017. So we're going to say for 2.5 years, this woman actually worked at the same place. At least. Anyways. It is known that learning rate is the most important hyperparameter to tune for training deep neural networks. This paper describes a new method for setting the learning rate named cyclical learning rates, which practically eliminates the need to experimentally find the best values and schedule for global learning rates. Instead of monotonically decreasing the learning rate, this method lets the learning rate cyclically vary between reasonable boundary values. Training with cyclical learning rate instead of fixed value achieves improved classification accuracy without the need to tune and often in fewer iterations. This paper also describes a way to estimate reasonable bounds, linearly increasing the learning rate of network for few epochs. In addition, CLR are demonstrated on CIFAR 10 and CIFAR 100 datasets with ResNet, stochastic depth networks, dense nets, and ImageNet dataset with AlexNet and Google LeNet architectures. These are practical tools for everyone who trains neural networks. Makes sense. So what is happening here is, let's just related works. Tricks of Trade. What is this book? Neural networks, tricks of trade. Is it available for free anywhere? Shit, man, I don't want to pay 6,000 rupees for some bloody book. Now, because this thing came out of US Naval Labs, I'm going to assume this thing is much more smarter than what usually comes out of other labs. Saddle points are small gradients in slow learning process. However, increasing the learning rate allows for more rapid traversal of saddle point plateaus. A more practical reason to as why CLR works is that by following the methods in section 3.3, it is likely that the optimum learning rates will be between bounds and near optimal learning rates will be used throughout the training. What are the parameters that it actually takes it? Yeah, so you have cosine learning, this thing. You have Tx, eta min, this thing. Okay. Set the learning rate of each parameter group by using cosine scheduling. When eta max is set to initial LR and T current is the number of epochs since the last restart in SGDR. This. Okay, you have a pretty big thing. Can you plot this thing? How is the eta minimum derived? When last epoch is equal to 1, it says the initial LR as LR. Notice that because the schedule is defined recursively, the learning rate can be simultaneously modified outside the scheduler by using other operators. If the learning rate is set solely by this scheduler, the learning rate at each step becomes this thing. Can you plot this thing? Eta min is 0. What is the eta max? We are given T max and we are given eta min. We don't know what is eta max. What is eta max? Get LR. This is LR scheduler. Base LR minus this thing. How does it compare to this? This is, you know what? Now let's start the research part. That's just basically reading a lot of papers and plotting the results. The usually the boring part. Import matplotlib dot pyplot as plt matplotlib in line. Okay, cool. Right, so you have this thing, you have this thing, you have this thing. Let's just write it the way I find it simpler. Now group LR is basically the whatever is the LR, we don't need this piece. So this is your function, right? So last epoch, let it be 1, yeah, whatever this value is. So self is now removed, self is removed. No, wait, what is last epoch? Last epoch, if last epoch is equal to 0, last epoch is what actually happened. Yeah, so this is actually tmax. Last epoch is going to be the x value that we'll use to get this thing. Self.tmax, import math, and eta min is actually 0. Self plus eta min 0. And so this thing now basically is, it can be written like this. Lambda. So cosine and SGDR is equal to lambda x, which is defined by this function x, and you need what is the LR. Okay, so we can do this SGDR list map this thing to a range. We can have zip because the learning rate is going to be fixed. So your LR value is always going to be 0.5 for now. Running this, you know what, for I in range T max LRs dot append is GDR, and you pass it value I and 0.05. let's see, plt dot plot LRs. What the hell, I'm pretty sure we did some, I think we did some silly mistake. Do they have a graph of how the learning rate actually varies? This is how they actually implement it. I don't know. Oh yeah, now it makes much more sense. Alright. So this is what it actually looks like. I'm pretty sure we did some mistake. Can we actually directly implement this thing? Let's not waste our time doing this. What you're going to do is we're going to simply do this. We need something to optimize, so let's just create a class no, let's not call that bobnet. Bobnet, what bobnet does is it is a super simple class. Yeah, bobnet, it is a simple class called nn.module def init self dot lin is equal to linear 4x4. Def forward is self comma x, return self dot len x bb, oh sorry, just call net is bobnet, and net torch dot random 1x4. Oh, perfect. And your optim is basically torch dot optim dot atom. It takes net dot parameters, and method object is not retrievable. Okay, perfect. Now what we're going to do is we are going to implement all of these schedulers, so we get a better understanding of what is happening. Alright, so you first start with this. We'll start with stdr shed sch is equal to this thing. It takes in an optimizer and a tmax, which is going to be 1000, this thing 10,000 optim okay. So what we now do is lrs dot get dot append sch dot get lr, and it returns a list. So we do this, and finally we do sch dot step. Okay, what if I do this? Man, I should have read what is the crash log. What was the warning? Tmax is not defined. See people should stop being stupid. Ah shit. Oh, so you can see you get a very beautiful curve. Yeah, so this is much better. This is a very beautiful curve. This is the curve that you get when you use cosine annealing scheduler. Should we create a single graph? We should probably create a very big graph of all the possible learning rate schedulers. And let's just, yeah, you know what, let's do this. Cosine annealing this thing, and you have, so we're going to append this thing. What we're going to do is we're going to fix it, like we're going to standardize this thing. Yep baby, standardize it. Oh cool. Now we're going to implement all of these different models, different schedulers, so we know what exactly is happening. For multi-step, step LR, and multiplicative LR. What is multiplicative LR? Function that computes the integer parameter, a list of such functions, one for each group. Yeah, we don't need that. We don't need that. We're going to use step LR. Step LR. It also takes in an optim, and it takes a step size, which is, let it be 100. Gamma is equal to 0.5 for simplicity. What you're going to do is we're also going to say this dot get LR 0. Perfect. X0 for X in LRs. You asshole. You asshole. What? Oh shit, we cannot do that because it is being used in the same optimizer. So what is step size? This means is every 30 equals, it has to reduce it. So if I do a step size of 200, it should reduce it by step size of 500. Okay, so apparently we cannot do that. But what we'll do is we should make this graph. Now we should make this graph. So we'll need to do it the hard way. मेहनत करो, मेहनत का फल मीठा होता है. Step this thing. We have LR's cosine is this thing, and LR's dot append. We're going to do it this way. LR step. We need to add it here. Oh, sorry. Maybe it would work. Let's see. Oh, so it does not work. Let's not get ahead of ourselves. We have this thing, and what we're going to do is we're going to do this thing now. No, you asshole. It's not working. Step size is equal to 30. Oh, what just happened? Oh, now it's going to work. Yeah, that's what we're talking. That's what we're doing. We do it this way, people. Okay, so we'll do it this way. Label is equal to cosine annealing LR. Label is equal to step LR. plt.legend, because this is the stuff of legends. plt.figure fixed size is equal to 10 cross 10. You know what, let's just make it 10 cross 8. Yeah. Perfect. Now we get a better understanding of what exactly is happening here. Right. And so what we'll do is we'll need to always initialize it. So let's just put it here. Now what we're going to do is we're going to try the multi-step. Multi-step is basically the same thing. Let's not waste our time doing that. We'll try the exponential LR. What exactly is this thing? Expo LR. It needs the optim, and it needs 0.1 because that's the gamma we're using everywhere. And what we're going to do is it's going to say this dot step, and we'll need another thing called LR's expo. Huh? Float must be a string or a number, not exponential LR. What? Oh, sorry, mate. Let's not do gamma 0.5. Let's do gamma 0.1 maybe. Ah, now we're talking. Okay, and gamma is equal to 0.99. Step LR, step size is equal to 250. Gamma is equal to 0.5. Cosine annealing. What are the defaults here? You have eta min is equal to 0. Ah, see, this is good. This is good work. We should do things like this. So if someone is confused, they can simply refer to this thing and we can get popular people. Okay. Various learning rates and the plots. Rate scheduling methods. Okay. So you have this thing. What is the next thing we have? We have already achieved this thing. We are going to do LR. No, we can't do this because we need something to actually do this. This is the one I was talking about, the cyclic LR. Oh yeah, let's do this. Cyclic LR. So again, this thing. You need an optim. You need a base LR. Let base LR be equal to what is the final value of cosine annealing? Oh, sorry, my bad. 60 minus 10. Let's just call it 0.002. Base LR 2e minus 4. Yeah, max LR is equal to 1e minus 3 and step size up. LR's cycle dot append cyclic LR dot get last LR 0 and finally dot step. E is not defined. Oh. Optimizer must support momentum with cycle momentum option enabled. Says the rates of each parameter group cyclic learning rate policy. This policy cycles a learning rate between two boundaries with constant frequency as this is this. The distance between two boundaries can be scaled on per iteration or per cycle basis. Okay, so optimizer must support cycle momentum. Should I do this? See, let's just do an SGD. Nestrov. Cycle momentum. Optimizer must support cycle momentum. Says momentum is equal to 0.9. Oh. So the step size up needs to be equal to 100. Okay. So the base LR is equal to 2e minus 4. Max LR is equal to 1e minus 4. Oh, sorry, 3. And we have step size up. And you know what? That's pretty well understood. Step size is up is 200. And now what we need is mode. Mode is equal to triangular. See, this mode is triangular. Now what other modes can we actually use is we have triangular 2. Oh my god, do we need this thing? We'll need like multiple lists to handle this thing. LRs, cycle 2. You'll need to do this whole process. Oh my god, this is painful. Triangular 2. Okay, so in triangular 2 it actually starts to, what should we say, it actually reduces, and the final version that we have is exponential range. So yeah, what if we do atom here? Does it work with atom? Momentum, no, it does not work with atom. SGD, we also add SGD, we add atom, we add atom, we add atom here, so we know that this is for reference. Okay, and finally we have the exponential range. So let's do this thing, and you have basically LR cycle 3, 3. You have this thing. To reduce the overload, let's just say yeah, so this, I don't know if foreigners use this shit, but this is basically Indian sign of saying that, you know, it's basically just a copy of that thing. Last cycle 3. God damn. So you know what, let's just do this. Exponential range. Alright, so we have this thing, and I think the final one that is left is one cycle LR. I think one cycle LR is actually the coolest. You don't need the cycle 3 now. Fuck cycle 3. Fuck cycle 3. Okay, this is done. You have the optim and you have the max LR, which is equal to 1e minus 4 to ensure consistency. Sorry, 1e minus 3. And total steps is equal to T max, and you have one cycle. So what this thing does is that, you know, pumps up the cycle rate to a particular size and then starts to decrease it. LR's one cycle. Total steps. Oh. Should we do it on Atom? Atom got unexpected. For consistency, we're going to do it on Atom. This thing is LR's one cycle, and we do this thing. We say Atom is this thing, and max LR is this thing. We need to remove spaces where we can, so we can actually put them all together. Somebody who is going to put in the effort would anyways understand what all this is. See, this is a beautiful curve, people. And lastly, we have cosine annealing with warm restarts. Let's be just done with this. Yeah, let's just do this. We're going to complete this piece and then we're going to take a break. What this is, it takes an optim, it takes T0, which is T max. Yeah. And we're going to repeat this entire thing. The only thing is that we need underscore WR. Similarly, we'll do this whole thing here, and the only difference is we need to do WR, get last LR, much better. And yeah, so we do this and we do this. So T0 is going to be 2. What does? Okay. So this is a bitch. What is this thing doing? If I don't do this, do I get the correct graph? What is the blue one? What? Why is this stepping? Even smaller. Even smaller, even smaller, even smaller. No, it's the same size. Why are you so big? I'm sorry. We'll also need to do this. It's so painful. And benchmarking is not an easy task. Right. To do this, do this, do this, do this, do this, and do this. And you can see what kind of thing happens. So Tim Max is going to give the oh man, forgot this. So now this thing is fine. We'll update this now. I'm completely pissed at this thing right now. Okay, this thing is done. It's still not done, you asshole. Alright, now it is done. This thing, this thing, this thing, this thing, this thing, this thing. Much better. Okay, so at Tmax, you basically, okay, so we haven't added this thing either. Okay, so you're getting this pink value with cosine annealing. Yeah, so when Tmax is equal to Tmax, it's basically the same thing. So if I do 2, now you'll see what exactly is the difference. Yeah, you can see this thing now. Let's just do 10. So what it does is, if it is the same value, then yeah, it's the same. So in this case, Adam, and we say T mult is equal to 1. Now what I can do is I can actually take T mult and basically can make this 0.6, so it'll be much more clear to people. This is 2, this is 2. Yeah, that's it. Fuck you. Yeah. 2, 2, 2. Alright, so now you can see what exactly happens is each successive iteration is actually 2 times longer. Oh man, oh man. Oh my god, I'm tired. So let's just let's save this thing. Let's put it on some blog or something. You know what, let's just put it on LinkedIn, see if anyone finds it helpful enough to actually use it. Okay, so I'm going to take a break now. Let's play some music. I'm going to mute you people. Sorry, mute myself. I hate Tarak Mehta Ka Ulta Chashma. Why does it recommend me this thing? The music we are going to listen to is, we're going to listen to Slash today. Shadow Life. Pissing off Michael Jackson, that's something. Sweet child of mine. As I'm going to play this music, you guys should probably just skip the next 7 minutes. Yo. Okay, back to it. So I have one doubt, which is in cosine annealing and cosine annealing with warm restarts, the learning rate actually starts much lower than what we said it should start at. And now I get why you would prefer like multiple restarts values, like with this thing, cosine annealing with warm. Basically, why would you prefer a restarting? Why would you prefer a restarting? What should I say? Learning rate scheduler, and not just one cycle LR, because in one cycle LR I've seen that it goes to one very good value and then it starts to decrease. Yeah, man, this is good. It's good we did this. Well, let's just keep this thing this way. So for future reference, what else do we have to do today? Yeah. So what we are going to do is we are going to support cosine annealing with warm restarts, and we are going to support cyclic LR. So we did this because we wanted to know what are the two learning rate schedulers that we are most often going to use. So yeah, if config.scheduler is this thing is equal to cyclic LR, we get this. Elif cosine.scheduler is equal to this thing, then we have scheduler is equal to this thing, and we are going to get these values from here. Okay, no, we are not going to do this shit now, and we are finally going to say else, oh god, else scheduler is equal to none scheduler, and if this thing, if that's it, if scheduler, we do a step. Now the values we need to actually put this the cyclic LR are these values. With cyclic LR we need to use SGT. Yeah, so we're not going to support any of that. We're not going to use multiple schedulers, multiple optimizers. That's just too much of a pain. So we're only going to use this, and what we're going to use, say, is, yeah, we only support this thing, and for this we need the values, which are these values. Okay, optimizer is equal to optimizer, this thing is equal to the total steps, how many times you want to restart, upon basically config dot n restart, t0 config dot t0 diff. Okay, let's just call it this thing. This is a horrible name, but let's still do it. And config dot tmult, and we need to add this check here because I know I'm stupid and I'm going to mess up at some point of time. if self-start scheduler is equal to cosine, if self-start scheduler is equal to this thing, self-start assert has attr self t0 mult, provide this if using scheduler, and the second thing we need to ask is, sorry, not t0 mult, t0 dev. And the second thing we need to say is, where is it t mult. Perfect. So yeah, we know that we are going to get this value, and eta min is equal to 0. The scheduler becomes this thing. And so this is the only scheduler that we are going to support right now. Yeah, let's just do this. And you know what we are going to do is we are going to hard code these values here. So, and this is where this current graph comes to use. What we have seen is the scheduler actually, it works very well, but the problem comes when so around 5k we would like to have a restart. We do not want it to reach the epitome, we don't want it to slow down. So well, even if it slows down, it will learn again, right? So if we are going to iterate over 26,000 steps, which is I think I mentioned this thing here, yeah. So yeah, whatever. Let's see how much saving I'm getting now. Still the same. So yeah, that was stupid. I would get the same as the factors would get divided off. Yeah. So if I have this, say I can just draw, let's just play around with this value for now. And what we're going to do is we're going to do this thing. And whatever parameters you have, it's fine, it doesn't really matter whatsoever. What we need to see is after how many tokens should we actually restart this value. plt.plot cosine annealing, no, we need this thing. Yeah. Oh my god. 3 minus 4 cosine annealing. Yeah, it's so if I use 0 comma minus 5, which is a pretty strong learning rate, 5e minus 3, it's a pretty big learning rate. Then if I do 5, it is just 5 cycles. I would like to iterate 3 times. Yeah. So what you're going to do is you're going to set this thing at 5 and tmult to 2. this thing is equal to 5 and tmult is equal to 2. We would like the next step to be twice as long. Now I understand that this is not a very good way to do about it. This is still my gut feeling, but whatever. Okay, so we added support for this particular function. Now what we're going to do is we're going to add support for, so you also have exponential learning rate. We do not want that, because with language models you like to see the value going up and up all the time. With cycle LR, this is good that it does not go as up, but the problem is that it we need to use SGD, and I don't know much about SGD. With warm restarts, let's just use this method for now, and that's it. Let's just add support for another one, which is one cycle LR. Yeah, so elif scheduler config dot scheduler is equal to one cycle LR. We are going to say scheduler is equal to all these values, which is this optimizer is equal to optimizer, max LR is equal to config.lr, and total steps is equal to total steps. Okay, so we support two learning rate schedulers. Let's just add this thing here, scheduler which will literally use of these two things, which is this to this, or we have this, this to this. Okay, so we have these things. I think we're in a pretty good state now. Yeah, what else? Yeah, let's just commit this. Git commit add support for multiple schedulers. Oh my god. Alright, this thing is now in a pretty decent state. So let's go back and read these papers a little bit more efficiently. Alright, so cyclic rates are basically it's the same paper. Alright, so now with cyclic rates, we see what this cyclic rate thing does is it fluctuates the values, but it fluctuates the learning rate between two values, and so it is expected that the model, because it is fluctuating between two values, these values can be good, and so we can say LR will always be between the optimum values. Okay, they also show that Nestrov works better. And actually the model trains faster, and this is what we need right now. We need the model to actually train faster. Not just better, but actually faster. Image.Alex, as the learning rate increases, you see that up to a certain extent it gets higher, but after that there is, okay, this is this looks like one cycle LR. Okay, and here we are saying as soon as it enters the second iteration, the values start to improve, and the triangular 2 actually is like a little bit better than fixed one, but we'll take the trade-off. Anyways, we are not using any of these, so it's completely fine. See how the learn accuracy also like oscillates. Again, they show as the learning rate increases. This thing too complicated. So this paper is super convergence, very fast training of neural networks using large learning rates. While deep neural networks, in this paper we describe a phenomenon which we named superconvergence, where neural networks can be trained an order of magnitude faster than with standard training methods. The existence of superconvergence is relevant to understanding why deep networks generalize well. One of the key elements of superconvergence is training with one learning rate cycle and a large maximum learning rate. Okay, the primary insight that allows superconvergence training is that large learning rates regularize the training, hence requiring reduction of all other forms of regularization in order to preserve an optimal regularization balance. We also derive simplification of Hessian-free optimization method to compute an estimate of the optimal learning rate. Experiments demonstrate superconvergence for CIFAR 10, 100, MNIST and ImageNet datasets, and ResNet, wide ResNet, DenseNet, and Inception architectures. In addition, we show that superconvergence provides a greater boost in performance relative to standard training when the amount of labeled training data is limited. The architectures replicate this work will be made available upon publication whatsoever. So what is in comparison of test accuracies of superconvergence compared to a typical piecewise constant training regime? Wow, so learning rate goes till 3. That's impressive. So again you see that the accuracy actually increases, and while the learning rate is increasing, but after that it only increases, it goes through a rough period and then it again starts improving as the learning rate decreases. Oh, so even before completing before doing one complete iteration, you're getting pretty good accuracies. So at step size is equal to 3k, it's pretty good. It shows it has the 92.1% accuracy. What that means is that just 60% of the data set, which I'm assuming is 5,000 images, 60% CIFAR 10. So let's just see. $60,000 images. So approximately 5,000 images. Oh, so 5,000 images is 60,000 images is for, might be 55,000 images might be for training and 5,000 images for testing. That might be the case. So at just step size is equal to 3k, it was able to give 92.1% accuracy, which means if I have very small or limited data set, this is what I would use. Again, in all these cases, what you're seeing is the learning rate, the accuracy increases pretty rapidly, but then decreases, or it goes through a particular rough period. So you see the rough period here, and then starts to improve once the learning rate, the gradient of learning rate actually increases. So in this case, you can see that while the gradient of learning rate is increasing, these models are performing very well. these also increase. But the moment gradient of learning rate starts to decrease, these models also start to perform a little bit worse. And then again at the bottom you can see around here, around 25%, the 75% mark, not even 75%, approximately at 65% mark, the gradient of learning rate again starts to increase. Yeah, I mean, this is where you might see the exponential curve do better, because in this case the gradient of exponential curve, the gradient of learning rate is always increasing. Yeah, am I right? Yeah, the gradient is always increasing. So this is the learning rate, this is the accuracy, typical learning rate range, test result where learning, there is a peak to indicate max LR. Why is it going, learning rate increases? I don't get it. Superconvergence. In this work, we use cyclical learning rates and learning range test, which were first introduced in your own paper and later published in your own paper. To use CLR, one specifies minimum and maximum learning rate boundaries and step sizes. Now, please note that the philosophy behind CLR is a combination of curriculum learning and stimulated annealing, both of which have a long history of use in deep learning. I find it super annoying that in DL there's so many learnings. Gradient or steepest descent is an optimization method that uses slope computed by the derivative to move in the direction of the greatest negative gradient to iteratively update a variable. Hi. Oh, this is why they need very large learning rates. So you can see this thing learns pretty well. It's horrifying things to see. This is the beauty of it, that in just one data set it is able to, just one iteration it is able to learn so much and so well, which takes these other algorithms like 8,000 iterations. Oh, 80,000 iterations. Okay, so which means this is approximately how many epochs you have? This is 10,000, so this is 2 epochs. In 2 epochs it is able to reach a pretty decent accuracy. Okay, let it be. Finally we have SGDR. This thing is going to take 2 hours to process. So let's do one thing. I'll start my visualise.ai machine. So we'll let this thing run and we'll see what happens. Oh yeah. Yeah, I'm not going to read any of this, man. Probably later. Alright, so we have done this piece. What else do we want to implement? We have done yes, this is like my task list I wanted to complete today. So we have done this much. We should add W and B. I'll probably do it later. And this is denormalized layer. Another thing I wanted to see is how does different combination of loss works for different methods. Wait, so I'll just put on my machine. I don't want you guys stealing my tokens. Alright. Yeah, so I was listening to George Hartz, and what he was saying is the way normalization works, like batch norm or layer norm, what they do is they calculate the mean and variance of your input data set, and they convert the output which has mean 0 and standard deviation of 1. But you could also do it the other way, that you could assume that the input is actually has a the input has so you can assume that the input has mean 1 and variance 0, and then you can spread that data set. This works particularly well for regression tasks. We'll probably also need to update our README for all the things that we have added. That's my wallpaper, people. What else? Yes, I wanted to see how different mixture of different loss functions would work. So we're seeing, so consider this particular example. You see that the loss function here is the value does not decrease. The value is pretty low compared to the actual loss function. Oh my god. Yeah. Compared to the loss function here, loss value here, it's pretty small, so it's always below 1, but these values are way above 1. So is it possible that if I combine two like lambda 1 plus lambda 1 loss this plus lambda 2 loss this, it would actually learn well. So I need to study this thing. Yeah, another thing I read was, so I ran a lot of iterations of MCTS, and in each of these iterations it was always picking up one particular value, as we saw in our last experiment. So you see, I didn't fix this thing, but it's always picking up E2, E4, and this is not a good thing. What we would like to do is we wanted to pick a lot of different values. So the way they handle, the researchers at DeepMind handle this thing was at each input they added a particular noise. Yeah, so you can see this. The Dirichlet noise dir alpha was added to the prior probabilities in root node. This was scaled to the inverse proportion of approximately the number of legal moves in typical position to value of this for chess. Unless otherwise specified, the training and search algorithm parameters are identical to alpha. Yeah, whatever. It's so slow. Let's study about this thing. What is Dirichlet noise? What kind of noise is this? Oh, actually says this thing. In probability statistics, Dirichlet distribution, often denoted as DI alpha, is a family of continuous multivariate probability distributions parameterized by vector alpha of positive reals. Okay. Guys, we are going to actually cover another paper probably later. I really wanted to cover this thing when I thought we would scale our entire data set to 300 million games, which would be approximately 300 million cross 83. That gives you 24.9 billion moves. Yeah, so this thing is started. CD chess lm git status, git stash. How many stash do I have on this thing? It's crazy. Just one thing, I just want to check a couple of bugs. Config.lr, lr. I don't want to have a learning rate. That's right. Okay. Do a git pull. Okay. Now Python train.py -- name a4. No module name transformers.modeling GPT-2. Import transformers. Transformers GPT-2 LMS. So this has all the they also have updated the documentation. Transformers. Yeah, I need to figure out some other way of actually getting this thing out. Transformers dot, let's see, what are the suggestions? Generation, modeling, TF, utils, optimization, transformers dot models dot something, GPT-2 dot modeling GPT-2 dot, give it to me. No, from import. Now it's going to give me suggestions. I'll try to. So it's saying we import block. Oh, this is the first thing into code, and I should probably update my local code as well. Malapha. Oh. And I need to update my local code as well, and the version I'm using pip3. Install transformers -- upgrade. Oh boy, go. No, what's up? Let's see. So it has it created? No, it has not created a particular folder. Using numpy zips, you'll see how fast this thing actually loads compared to what was happening previously. Load boy, go boy. Oh my god, I was using 3.1. So you see, it's loaded the entire data set to memory in 14.3 seconds. None type object has no attribute LR. Oh, because the scheduler by default is initialized to none, whereas it should have been initialized to cosine annealing warm restarts. Oh boy. Also, why is it saying none type object? Oh shit. We'll also need to improve this thing here. If scheduler is not none, models.a4 delete. Delete this thing. NumPy zips. It took 15 seconds to load the entire dataset on memory. See, that's a good speed. That's a very good improvement, man. Over what it was taking 16 minutes to actually load it. Provide this if using, see, actually flags work. mdiv. What the fuck? You don't use any of this. Use T0 dev, not T0 mdiv. Good thing is, it did that. It found that issue while it was initializing the values. Ah shit. We didn't update this thing here. Need to update it here as well. T0 dev, and here is T0 dev. So the model size is now this thing, and also this is a new model that we are training. Damn, look at the loss, man. Holy shit. Why are we getting, oh my god. Holy shit, man. But as the loss starts to decrease, the accuracy also decreases. While we are having large loss values, the accuracy, we do get better than zero accuracy. Let's just say it like that. This is a very weird model. Why are we getting such humongous loss values? Did we do something wrong? So you have beta. Yeah, you use the policy loss here. It's basically the same things. And we also added the tanh, which means the loss was actually coming from policy, which is true because we are using cross entropy loss, and cross entropy loss can give you pretty big loss values if you don't use it correctly, like here. Let's just download the current tensor board. I mean, I know this is pretty I'm behaving bad. I should let it run. I should be patient, but I'm not. So that's it. This thing blows everything away. Like, none of these things would make any sense in front of A4. This is test. This is and so the loss value is pretty huge. Okay, let's just let it run. Whoa, so the total loss, as I said, the policy loss was so huge. If you do it like this, now you get a better picture. This is like 2 orders of magnitude over what this particular value was. We're going to let this thing take its own course. You see the loss is now pretty stabilized, still moving around violently, and that is because loss is now good, but the reason it is moving around so violently now is because the policy, the value for loss, that is moving, that's changing very rapidly. That's why you don't see smooth loss here. But let it be. We'll let it run. We should not be so greedy. Okay, what are we doing? So let's just first copy paste all the changes from here, or you know what, it's better we'll just push from this terminal itself. Wait, what? What have we changed? Oh shit. Alright. Small code is updated, so is train.py code. Oh yeah. See, the speeds that we're getting are also pretty decent. It's 1.54 iterations, as I said. What we're getting earlier was like 1. Sorry, just the one above this. Here, I was probably here. The ones we're getting before were like 1.25 or something. So because of the this is because it's not going around and reading from the disk again and again. We should probably add some kind of a regularization on our weights, because this is what they also add in language. No, so they do add, so all these large models, they do add what should we call it, some kind of a regularization on weights. This basically shows that it's heavily biased on what were the recent news articles of Modi, BJP, Pakistani, why Africa, I don't know, but whatever. Islam, terrorists, non-Muslims, Christians, etc., etc., etc. Blacks, it gave a pretty bad score. LOL. Meh. For Indians, it gave a pretty average score. And imagine doing unit testing for GPT-3 model, like how many things you actually have to consider. Again, getting a pretty bad accuracy. Getting bad accuracy, but how's the loss doing now? Let's actually download this thing again and see. Where to go here? Where's the folder? Now we're seeing that the value loss, it's actually pretty consistently high. Man, this is frustrating. And boom goes my laptop. Again, you see, while the loss was very high, you were seeing that there was a certain accuracy to it, but then the accuracy eventually hit the value 0. See, if the loss is not decreasing, it's probably not going to decrease further as well. I mean, learning rate, where is learning rate? Learning rate starts out at 0.05. What if the learning rate started at 0.005? We kill this process, it's 249. And if I do training 0.05. Let's just call this model A5. I was also wondering if we could add weights and biases support to this thing, like if it could just log everything to the cloud, and we would have been able to just see the tensor board online, because that's a problem, right? I can't see the tensor board here. That's true. Log in. I'll probably log in on my other computer, the main browser. The collab. Who likes to use collab? Let's add this thing. Let's add weights and biases. I have already logged in. Okay. Define a sweep. So I need to log in from here. Let's see how the login works. To get a profile, you know what, let's just put this thing here. First I need to authorize. Man, I don't want to share this thing on my live stream. I don't want to change my tokens. Alright, how is this thing going? So I can log loss. I can log anything basically, right? I'll run this thing once and let's see what happens then, but I need to do that not on my main screen. Pip install w and p. This installs it immediately. W and p login. Alright, so clearly does not work here. I need to do that on the main terminal. W and p login. Login. Right. So I copy it from here. I do this thing again, login, control V, paste. Okay, so appending key for API.NET.RC file makes much more sense now. What we're going to do is we are going to add whenever we're going to run the training code, we need to import this thing. So import this. Import WNB. We do an init. Config is equal to config. Trainer.train. We do this. Config is equal to. We'll just pass it the mega args function. Config is equal to args, and here we need to pass it all the args. So this way we are always sure about a lot of things. We can log this all, and next thing we need to do is we need to add WNB watch model and model.train. Start training it, and we're going to log it every time we log this. Okay, so there are three things that this piece needs to log, which is last total, which is this, log policy, which is this, and loss value, which is this. And yeah, I think that's it. Gradient metrics and the graph won't be logged till the forward and backward paths have both been called. So we need to add this thing here. Images. Okay. This should work. I think so. And the way you would go about it is no, we don't want any sweeps. No, we don't want any sweeps whatsoever. Set train. No, we don't want it to we don't want it to do something like this either. Now it's a public project. It's Blindfold chess. This PyTorch. Oh god damn it. Also need to do a W and V init, which we can do here. Alright, so clearly this thing is not improving as much as we would have expected. So we're going to kill this thing. And we are now going to use the... No, I don't want to save the model to the memory, it's fine. Man, you people are going to steal my tokens. Uh, 2595. Kill dash 92595. Alright. This is done. Now we are going to use the W and B for the first time. Let's see what happens. This thing ain't learning anyway, so why don't we just delete this shit? A5. Invalid syntax. Line 234. 234. Oh. Sorry, sir. My bad. Let's see. We log in. Logical pyramid 1. NumPy zips. Wow. Does this like spy and shit on me? Will it do that? Holy shit, it logs the GPU temperature in Celsius? Seriously? GPU, oh my god, this shit is... Oh, this is good. Oh, this is good. Oh, this is good, man. This is good. I like this. What else is it logging? Model. Okay. Yeah, well, that's fine. And it's not going to gather this thing as well. Oh my. Oh, this is good. Oh, this is good, man. This is good. I like this. What else? Can I like scale these values? Oh, it's automatically scaling it for me. Okay. This thing logs updates every 20 seconds. Process memory available. Memory in use. Non-swap. System memory utilization is at 72.70. Oh boy. GPU utilization is at just 33%. GPU's time spent accessing memory. This is good. I'm impressed. Pretty damn impressed actually. This shit. They were right when they actually mentioned magic. They were right about it. This is good. Now at least I don't need to keep on now I don't need to keep on downloading these things, the tensor boards. So we'd also like to log if we have the scheduler. If scheduler is not none, then so what we're going to do is we're going to do something like this. Log det is equal to this thing, move accuracy is this thing, and logged det dot update. We're going to have LR as last LR is equal to this thing, and last LR is equal to this thing, and we're going to log this entire dictionary. And we would also like to log this value, the test values. But that's fine. I don't need the test values. Oh, we smoothing the values. Now it's better. See, man, these are just basically tensor boards, and they're so good. See, this is just a tensor board. But this is such a fancy tensor board. This is neat. This is good work. Yeah. Do they have a mobile app? Wait, oh my god, people are going to steal my tokens. Weights and biases mobile app. 14 alternatives to lobe. What is lobe? Floyd. Yeah, I know about Floyd. What is lobe? Let's go to website of lobe. Lobe. Machine train apps to identify plants. Lobe helps you train machine learning tools with free, easy to use tools. Yeah, see. When you're done, you can export a model to a variety of industry standard formats and ship it on any platform that you choose. AWS, TensorFlow Lite, Azure, Onyx, Flame. Oh, this is cool. What should I say? UI. I'm actually going to just save this because the UI is so cool. Choose on the folder, new folder, cool UI. I'm going to save this thing here. Floyd is it's basically Floyd Hub. Ah, man. Oh my god. I don't think I can ever go back to not having weights and biases. Unless I have custom tensor board. Then I would like to have my custom tensor board. Your focus on science will handle the version control environments. Really? You're going to do so much for me? Again, take it. What these companies do, and this is like my big problem with all these big companies, what they do is they take a product, an open source product that is already very good, and then they charge you for it. Just like what happened with MongoDB, what happened with that other DB company, there was this fight. MongoDB licensing, Google licensing fight. Yeah. Dark side. So they came up with something called the server side public license. What that means is sometimes, especially in Asia, taking its open source go offering hosted commercial version of the database and using it. See, this is what I'm talking about. If you're going to use a good open source project, to credit them, tell them, pay them if it's possible. Paying someone is the best way to get your shit done, because if you're going to pay someone, then you know there is no alternative to weights and biases, boy. It's not true. You do not have an alternative. See, the loss keeps decreasing, but the value loss is not. What happens if I do a new run? One visualized. What does this mean? Blue. Can you give it any color? Give it pink. Oh, this is neat, mate. Oh, this is neat. System. It is GPU power usage, memory allocated. So it's using like 80% of the GPU. You can if it's let's do an NVIDIA SMI. We can probably pump up our batch size to be about like 350 or something. See, right now it's only using 75%. Oh boy, that's a bug. No, it's using 70%. So if 270 is 70%, then you can add almost 40. You can possibly do 40 plus 40. I guess you 350. You can probably do it at 330. You know what? Let's just scale this process. NVIDIA dash SMI. Oh, sorry. It's tab. We're going to have another terminal open for all the other purposes. Yeah. So you do a PID train dash name 144676. So what we're going to do is we're going to kill this process. Kill dash 94676. This should clean this up. Okay. Now let's see. What is it saying now? I can stop this shit from right here. Well, that is neat. That is good. That is actually very good. If there's some way that this kind of thing would load faster, I think that would be the way to go, man. Yeah. So now what we have done is we have improved the logs that we want to take, which is the loss total, and we also want the learning rate, and we update this dictionary here. So what we're going to do is we're going to just delete this thing, and we are going to restart the training with a 5. Is there something I'm forgetting? Yeah. So batch size is 330, and yeah, let's see. Oh shit. Do you think it can handle 30 more batches per card? So 70 at 270, so you have 270 batches, which means each GPU has approximately 135 batches. 135 is 70%, which means you can say 10% is approximately 20 batches, and so we can add 40 more batches. So not this, but we can do, you know what, let's just make this thing 300. Let's see if this thing runs. And if I don't want something, can I just remove it? Let's see. Cool fire. Alright. Much better. So yeah, now we're logging all these values, and our GPU memory allocated percentage should improve now. Yeah, so it is taking more batches in, but it's only 75%. I mean, it should have been more. Let us pump this thing to, let's just increase the batch size to 330. And what we're going to do is we're going to experiment with killing this process from here, and then let's see what happens. If I do a stopping from here, it's not really matter anymore. It does not work anyways. So what we are going to do is we are again going to kill this process, which is 7178. No. Which is 7178. We should clean this up. Very good. And now what we're going to do is we're actually going to delete both of these runs. This one. So yeah, let's take a break. Let's just run this thing one batch, and then I'll just leave it at that. Let's see. Train.py, it is at 330. Use summer shape. What percentage are we getting now? Oh, we can still go up. Oh, it's good news. We can actually pump this up even more. So it's right now at 9,000, 9,600. We can take this thing to all the way to 380. So we're again going to kill this process. We're going to go to edge tab, and we're going to kill this 7524, kill -9 7524 24. Alright, this should clean this up. And what we're going to do is we are going to delete this run. Yes, delete it. We have pumped up the batch size by 30. Let's see what if we take, let's take this thing to 400. This was initial learning at 270. Now we're going to take this all the way to 400. And as far as the name is concerned, I'm no longer really bothered because Graceful Universe 4. Does it train? Does it train? Does it train? Do I get a GPU mirror? Oh, it's training. What's... And actually add even more. We can train it on even larger data set. CPU memory allocated. It's already 3 hours. How much work do we have left? So we have completed all this work, all this much. We'll probably go over this thing. And now that we have the automated testing piece, $109. I think this is good enough, man. I think this is a pretty decent load. We'll probably pump this up another 1 batch, another 10 batches. A-9, we get 7689. Kill -9 7689. And we're going to delete this run as well. And what we're going to do is we're going to run this thing all over again. I think, you know what, that's it for today's stream. We'll just see how much we can, what is the maximum amount of memory you can put this thing on. It just eats it up, man. We can add another 20 bats. Come on, we can do this. We can do this. Let's just kill this thing. Kill -9 7956. Oh, 7956. Yeah, here this thing gives oh, it's not dead. 7957. Do I have to like manually go and kill each of these processes? Nah, it's done. Alright. And we are going to delete soft thunder. And we're going to train this shit again. The largest goddamn bat size you can create on this machine is... That's a lot, man. I was stupid. I should have checked this thing first. This is the first thing I should have done. What is it saying? What I'll do is I'm going to create a new token and I'm going to redo this thing. Settings. I delete this. Copy this thing. It says WNB login. And be login, re-login. Alright, cool. I'm gonna train this shit again. Hopefully this time it does not crash. It distributes this thing pretty well. In fact, I can actually go even larger layer right now. Even larger batch. I can possibly put in 20 more batches. 450 override. That's it, bitches. 450. .69. Alright. Oh, this is good. Usually, larger batch sizes means better training. Okay, Okay, I think that's enough for this stream. We'll let the model run for another 1 hour or so. I'll see how long it takes. Now it's going to take 4.5 hours to run this thing. Earlier it was taking 5.5 hours plus. I think it'll still take 5.5 hours because we locked the training epochs. So yeah, this was a pretty long stream. We got a lot of work done. We created a new model, debugged it. We did a little bit of study on the LR scheduling, read a little bit of papers, and we finally started using weights and biases, which is, oh, that's good. That's actually very good. What we're going to do next is, from the next time, we are going to study about denormalized layer, about the different loss methods, and how can we actually merge these things and improve this thing with Dirichlet coefficient, or basically Dirichlet noise. And we'll write some testing scripts. Okay, so toodles and have a good night.